In 1899, in Hilbert's first edition of that work, these axioms were actually formulated in a natural language, in this case, of course, German, right? So you'd have actually sentences like that, right? But at the same time, and earlier and later, there were a number of other important developments which sort of hopefully show that the axiomatic method was very much at the center of mathematical and scientific thinking at the time. So for instance, there were axiomatizations of arithmetic and analysis by Dedekind, of set theory by Cantor and Zermelo, of geometry, of course, by Hilbert and some predecessors, probability theory by Kolmogorov. Hilbert around 1910 concentrated a lot on physics, so he gave axiom systems for kinetic gas theory, thermodynamics. He worked on relativity theory and so on. But the other important development, which is going to be of crucial importance for us, is that there were also a number of people who were interested in the axiomatization of logic. One of the first people, or the most important figures in that regard, is another German mathematician, Gottlob Frege, who in 1879 gave one of the very first precise axiomatizations of logic. And these were developed by people like the Italian mathematician Giuseppe Peano, the British mathematician philosopher Bertrand Russell, and Hilbert and his students himself, especially in the 1920s. So that by 1920 you would have a complete formalization of logic, which let you not just it wasn't just a formalization and an axiomatic treatment of logic, but it was also a new language into which you could translate all of these other axiom systems. And this language was an artificial language, that let you also make all of the derivations, all of the proofs of theorems from the formalized axioms be simple sequences of symbols, so that you didn't even need to understand a natural language like German in order to understand whether something can be proved from the axioms. So this logical calculus that was developed by Hilbert and his school could then be applied to all kinds of mathematical systems. Hilbert and his students applied them in particular to systems of number theory and analysis. You could formalize axiomatic systems or axiom systems as collections of formulas or sentences in an artificial language. And then you could make precise what it is for a proposition to follow from the axioms by giving a certain precise, rigorous system of derivations in a certain calculus from these axioms. So these derivations were purely formal sequences of symbols, and it was sort of a mechanical way of testing whether a given sequence of symbols actually counts as a proof. And that, together with some other encouraging results that were discovered by Hilbert's students at the time, led Hilbert to postulate a certain problem and to be very optimistic that that problem could be solved in a positive way, namely the so-called decision problem. And that is the question, right? So the decision problem is the question of whether, given any axiom system in such a formalized language, and any potential theorem, right, or any question, any proposition in the primitives of that axiom system, is there a mechanical way that will always tell you after a finite number of steps, like a computer program that would invariably always give you the correct answer to the question whether that proposition is a consequence of these axioms? So that's a logical decision problem, and as I mentioned, people were very much optimistic that it could be solved. There was a lot of work being done in the 1920s, both in Göttingen among Hilbert's students and other important figures in mathematics at the time tried their hand in it. Possibly you've heard of Kurt Gödel, another famous logician who made a contribution to the decision problem, a positive contribution. Frank Ramsey also wrote a paper on the decision problem. That's the paper that we now have Ramsey theory from, interestingly enough. So people were hopeful that this problem could be solved. But then in 1935, 1936, both Alonzo Church in Princeton and, well, in 1936, both Alonzo Church in Princeton and Alan Turing in Cambridge proved that he couldn't solve it. And that's what I'm going to tell you next. How did that happen? How did Turing show that you can solve the decision problem? So the paper in which Turing proved this was called, as I said, Uncomputable Numbers. In it, Turing introduced a sort of a way of making precise the intuitive notion of what it is to be computable. And he tied it down sort of in the first instance to the notion of what it is for a number to be computable. I'll explain to you in a second what that means. And then sort of he develops this theory of this abstract model of computing, of computing machines, which are now obviously called Turing machines. And then at the very end applies it to the decision problem and shows that the decision problem can be solved by a Turing machine. And together with a couple of sections that, in which he argued that what Turing machines can compute coincides with what can be computed, period. Right? Together with that, or with the thesis that anything that can be computed in any way whatsoever can be computed by a Turing machine, that is now called the Church-Turing thesis. And that, together with the fact that the decision problem can't be solved by Turing machines, is now taken to be sort of, or after that, this paper was taken to be a demonstration that the Turing machine can't be solved at all. You can read along, by the way, on these slides there on the Turing Lectures website, and this link here will take you directly to the Turing's paper if you want to read it. So Turing's paper is about computable numbers. So what's a computable number? So first of all, what kinds of numbers are we talking about? Turing was talking about real numbers between 0 and 1. Real numbers between 0 and 1 are numbers that can be written using an infinite decimal expansion. So it's 0 point and then an infinite series of digits. So for instance, 1/2 can be written as the infinite sequence 0.5000000 and so on. 1/3 can be written 0.3333 and so on. And then of course, pi can be written as 3.1415926 and so on. So pi minus 3 is 0.1415926 and so on. Okay? So because it's going to be simple and because that's what Turing did, we're going to pretend that these numbers can, well, we don't have to pretend. Most of us probably know. Those of you who don't know, you can look it up on Wikipedia under binary number system. You can also write these numbers between 0 and 1 as infinite expansions in binary notation. So where the only digits are 0 and 1 rather than 0, 1, 2, 3, 4, 5, 6, 7, and 9. And in that notation, these numbers, the numbers above, have different representations. For instance, 1/2 is just 0.1000000, and 1/3 is 0.010101, and so on. And even pi minus 3 has a binary expansion, of course. Okay, so every real number between 0 and 1 can be written that way, right? Which means there is a sequence of zeros and ones that represents it. And we want to call a number computable if that sequence of zeros and ones can be produced by a computing procedure, right? Obviously, it can be computed by a Turing machine.